So today we want to start talking about material interactions with the electrical field. Material interactions with the electrical field, and we're gonna study different kinds of materials. I mean, two main kinds of materials. We're gonna study conductors and what's called dielectrics. And dielectrics is really the underlying model of the theory. We will find out that even free space can be modeled as a dielectric. And that will lead us to the concept of polarization. Okay. So, yeah. So up to this point, Up to this point, the effect of material have been included in one way, right? So the effect of material has been included already when we introduced what's called the flux density vector. So this is describe the electrical field. So we have charges. The charges generate an electrical field everywhere at each point in space. There's a field. Right, and there is a concept of a medium. So the charges exist in space, could exist in free space, they could exist in air, so they could exist in liquid. So there's the concept that there are properties of the space itself according to the medium, what the medium is. And we already introduced that a bit by introducing an alternate description of the electrostatic field. So we had the E field, what's called the field intensity, force field intensity. In this case, E was proportional to 1 over epsilon naught, some constant. And then we just multiplied by that epsilon naught to get D, another kind of vector that's called the flux density. It's called a density because it turns out to have units of Coulomb per meter squared. Of course, this has units of Newton per Coulomb, and later on, after we introduced the potential, we introduced the units of volt per meter. Okay, so we already know that epsilon naught is used to quantify properties of materials or mediums. We will go deeper into what D actually is. It turns out D is in reality a polarization vector. And we will discuss what polarization is. So we want to start with conductors. What are conductors? Conductors are essentially mediums. So free space is just free space, right? You can, like wood is wood, whatever, but you have certain kinds of materials, like metals, copper, aluminum, whatever, materials that have what's called high conductivity, meaning they don't have to be charged materials. They could be neutral materials. But the idea is that the charges inside the material are free to move without friction. Right? So if you have a bunch of charges in a material that are free to move without friction, right? If the material is neutral, if it's a metal, for example, still it's fine because even though let's explore a metal, let's say copper. Even if all the charges, well, the positive charges are the nuclei of the atoms, right? So they're not really free to move. What I mean by free to move charges, it's the negative charges, the electrons. So the negative charges are free to move everywhere. So it could be here, it could move here, and there is no resistance to the movement of charges, but the total charge of the material is going to remain neutral, because the total number of electrons and protons does not change. But the electrons are free to move everywhere. Okay, so this is completely free movement of charges as far as electrons are concerned, right? So this kind of material is called a conductor, and it has interesting properties. If everything is neutral and the number of positive and negative charges is equal, nothing happens. It's just a soup of free moving charges. Forget about this molecular model. Assume that we were not aware of the atomic model. Assume that, hey, conductors, as far as we're concerned, it's the sea of positive and negative charges, and they're free to move. Whatever happens, the total charge inside the material remains constant. Of course, regular materials have fixed charge distributions, and what we've dealt with so far is fixed charge distributions. Okay, so this kind of conductor, where I have a sea of positive and negative charges that are completely free to move, is called an ideal conductor. Okay, now what happens if I disturb this equilibrium, meaning I take some charges from outside? So this is my conductor. It has a sea of positive and negative charges that are completely free to move, but then I inject 2 positive charges. Those 2 extra positive charges are free to move, right? So they will repel each other. There will be force between themselves, right? They're completely free to move without friction. They're going to start moving, and they're going to stop only when they hit the boundary of the conductor. So in a conductor, if you inject charges into the conductor, the charges are always going to end up in the boundary. Okay, the charges are going to stop moving only when they reach the boundary. Okay, that's one thing we can do to a conductor. What's another thing we can do to a conductor? We can apply an external electrical field. Okay, what would happen? So I said that the conductor has the property that it has an equal number of positive and negative charges, right? If I have an external field, what would the electrical field do? Electrical field means an electric Coulomb force, right? So there's going to be a force applied on the free charges inside the conductor, and there won't be any resistance to this force. So the charges in this conductor are going to move and distribute, right? So it will happen at equilibrium. What will happen is that all the charges are going to move until all the charges are going to move inside the conductor until we end up with a surface charge density. So we're going to end up with a surface charge density rho s. Right? So the field is applied. The positive charges are going to feel the field and going to move, and the negative charge is going to feel the field, going to move. Everything is going to be in motion. At a steady state, everything will settle down. What are the conditions for steady state? The conditions for steady state is that there should be no more electrical field inside, because whenever there's an electrical field, I'm going to have moving charges. Remember, this is an ideal conductor, so there is like a tremendous amount of free charge inside the conductor. We will never run we will never run out of free charges inside the conductor. But everything will move and settle in such a way such that there's going to be a concentration of charge on the boundary, and this concentration of charge on the boundary is going to cancel the electrical field inside the conductor in such a way that movement is going to cease inside the conductor. So the E field is going to be 0 inside the conductor. The electrical field lines are going to terminate on the conductor, and we're going to show that they're going to terminate at 90 degrees. Okay, so that would be the steady state, essentially. If you bring any conductor and apply it to an electrical field, you'll find charge distributions on the surface charge density on the surface of the conductor, right? And the electrical field inside the conductor will be 0. Like if you have a transmission line, one of those towers, right? And you bring in a metal ball, right? You're standing here with a metal ball, you know. What will happen is because there's an electrical field coming out of the transmission line, you will, if there's a way to visualize it, you will see a surface charge density on your conductor. So it'll be in your metal ball, there'll be like a charge density along the surface. And it will be time varying in this case because the field is time varying, right? But we're only dealing with the static. So this sort of charge is called the induced charge. So this is not a charge that you add to the material because the material is an infinite well. It's an ideal conductor. It's an infinite well of equally positive and negative charges, infinite sea of equally positive and negative charges. When you apply an external field, you induce a charge in the material because this field induces the charges to separate and condense, collect on the surface. Okay. So what are we are ready now to describe the general properties of conductors. 1, induced charge in conductor always is on the surface or always moves towards the surface. That's 1. 2, in steady state, meaning when everything settles, charges distribute on surface, on boundary, I guess we could say, such that E is 0 in interior, ET, which is the tangent field, is 0 at surface, right? Only field in conductor is normal to surface, right? And why is that? So I have my conductor. Let me zoom in on a boundary. So this is interior, and this is exterior. This is air, let's say. So we're saying that the field at the boundary, we established that the field inside the conductor has to be 0. Okay, the only field that exists because there is a charge density rho s on the boundary, rho s. There is a field on the boundary. This field has to be normal, E. ET equals EN N, okay? Has to be normal to the surface. Why? Because assume there's a field that's tangent. If there's a field that's tangent to the surface, that means there's going to be a movement of charge tangent to the surface. So there's going to be charge circulating. If there's a field tangent to the surface, a field tangent to the surface is going to move, shug the charges along. So there's going to be a circulating field along the surface. But this is steady state. This shouldn't happen. Everything should settle down. Everything can settle down only if E of t equals 0. Since the tangent field needs to be 0, that means the electrical field at the surface has only a normal component. So the electrical field at the surface will only be at 90 degrees, will always be at 90 degrees. Okay, so this is property 3. 2, property 3 volume charge density inside is zero, of course. If the field is zero from Gauss's law, so this is a conductor. I have a Gaussian surface. From Gauss's law, the flux of the field, E delta S equals Q enclosed. But if E is zero, so Q enclosed is going to be zero. Okay. So the way you would draw this, so I have my conductor, I have my external field. I would draw the feed lines like this. Feed lines would be coming in, terminating at the conductor at 90 degrees, coming in, terminating at 90 degrees, coming in, terminating 90 degrees, coming in, terminating 90 degrees, coming out at 90 degrees. So if you want to like draw or write a program or whatever, draw field lines coming into and out of the conductor, they will always look something like this. Right? That's why in like when we use metals, it's always in metals, it's always dangerous to have a pointy edge. If you have a pointy edge, that's more surface. So the field becomes concentrated. It's like, imagine you zoom this in, this is like a ball, right? So the field is coming at 90 degrees. So the field gets concentrated around those pointy edges. Right, and that's why when the people build lightning absorbers, they build them as a pointy metal edge, right? So that the field gets concentrated. And that's why if you have like a metal with high voltage on it, discharge happens towards the pointy edges, because the field, because of this nature of the field always coming in at 90 degrees, the field gets condensed around, concentrated around the pointy edges. All right, so there's a surface charge density at the end. What is that surface charge density? So let's zoom in, right? So this is something like this: interior, exterior, and I have En. Well, I can always use Gauss's law. So I can draw Gaussian surface, this cylinder, small cylinder. This has top surface area of delta S. The field in the interior is zero, right? So the Gaussian integral does not apply in the interior. In the exterior, the sides do not matter because there is no tangent field. There's only a normal field. So the only thing that matters is En delta S, right? That's the left-hand side of Gauss's law. The right-hand side of the Gauss's law is the total. So this has charge density rho S. Is the total enclosed charge. The total enclosed charge is going to be rho S delta S, of course, over epsilon naught. So this tells me that the normal electrical field is rho S over epsilon naught. This is how you relate the charge distribution to the normal electrical field. Okay, so this is volt per meter. This is the relationship between the normal electrical field and the conductor and the charge distribution, surface distribution on the conductor. If we can write it in terms of the flux density vector. So take epsilon naught to the other side, it becomes dN equals rho S, which makes sense. The right-hand side is Coulomb per meter squared. The left-hand side is Coulomb per meter squared. Okay. Notice how the conductor here, when we apply an external field, it gets fed the field lines, and then the field lines come out from the other side. Imagine this is a very nice property. Imagine that we take this conductor and we stretch it such that it forms a very thin wire. We'll end up with the same thing. The field is going to come in at one point, right? Because this is an ideal conductor and everything is going to move to the surface. It doesn't matter how long this conductor is. The fields are going to still come out from the other side. So conductors are really ideal materials to transfer electrical fields over long distances. So that's what happens with electrical generation. Electrical generation, you might have a machine, rotating machine, that generates some potential, some electrical field. And you want to take this from the point of generation, transmit it to a geographically far location. So what you would do is you would do a transmission line, build a transmission line. As simplest transmission line is just 2 wires. So what happens is that because this is an ideal conductor or close to an ideal conductor, the charges are going to distribute in such a way such that the field lines are going to appear at the end, towards the end of the transmission line, right? And this is how you can move electrical fields across large geographical distances. This is how power transmission occurs. If conductors does not exist in nature, I mean, transmission of electrical power would be impossible. Okay. Let's do an example. 4.113. Okay, so that's pretty much, I mean, everything we can say about conductors. Say we have a spherical shell. We have a shell or a ball. Let's say conductor material. Okay, that's a sphere. That's a ball actually, and then we know what the normal field is. The normal field is En, 100 volts per meter. The question is, what is rho s? What is the surface charge density? We already know this, right? Rho s is going to be epsilon naught En. Epsilon naught is 8.854 times 10 to the power minus 12 times 100. So this is going to be 8.854 times 10 to the power minus 10 Coulomb per meter squared. Easy. Part B. What is E and V, the scalar field, inside conductor if Vs is 10 volts at surface? So I'm giving you what the potential energy is at the surface. Okay. Here the assumption is that for potential energy is that at infinity the potential energy is 0. Always that's going to be the assumption when you because as we said, remember we said the potential energy is not unique. I can add any constant and I'm going to get the same thing. I'm going to get the same electrical field from it. So the potential energy is not unique. You can add any constant everywhere in space, but we always add a constant in a certain way such that V infinity is 0. So yeah, given I tell you what the potential energy is at the surface, and if the potential energy at the surface, the potential energy should be the same everywhere on the conductor surface, by the way. If you don't see that, I'll explain that in a bit. But say we know that the potential energy of the surface is 10 volts. What would be the potential inside the conductor? Okay, so recall that E equals minus gradient V, right? And the voltage between 2 points, VB minus VA. If you don't remember this, you can always go back from basic principles, right? So this is so this is minus integral from A to B E dot dl. Right? If you ever don't remember this, again, you can go back from basic principles. You can say integral from a to b, E dot dl. What is this? This equals, well, how do you show that this is true? Plug in minus a to b minus grad v dl. Take the minus sign out. It becomes a plus. And this we know from the fundamental theorem of calculus. This is just going to be VB minus VA. Okay, so just to remind yourself that this is true. So this is the potential difference. Inside the conductor, grad V is 0. Why? Because E minus grad V is 0, equals E. E is 0, right? Because E is 0, minus grad V is 0, so grad V is 0, right? Grad is a differential operator, nabla is a good differential operator. So the change, there is no, the potential does not change inside the conductor at all, no matter in what remember grad V is the directional derivative. If grad V is 0 everywhere inside the conductor, that means tells you in any direction, the potential does not change. That means that inside the conductor, the potential is going to be the same as the surface. So if the potential at the surface is 10 volts, inside the conductor, V inside is 10 volts everywhere. Okay, so V interior is 10 volts. I said another statement, implicit statement is that if I know the potential at what point, Vs1 equals 10 volts, right? At every other point on the surface, Vs2, the potential needs to be the same. So you cannot have different potentials on the surface. Why? Well, this is easy to see. If Vs1 and Vs2 are different, what does that tell me? Well, Vs2 minus Vs1, we know is equals minus E dot dl from S1 to S2. But we already established that if we move along the surface, we're moving along the tangent of the boundary. We know that the tangential component of the field has to be 0. So this integral will always be 0. So Vs2 will always equal Vs1. Right? For a conductor, it's enough to know the potential at one point on the surface. If you know the potential at one point on the surface, this will be equal to the potential on the whole surface, and this will be equal to the potential inside the interior of the conductor. So we can say that a conductor is an equipotential volume. It's like a plate of a capacitor. Plate of a capacitor, the whole plate has one potential. That's how earthing works, by the way. The Earth is so big that it could be considered an ideal conductor, right? The Earth is like an infinite sink of charges, right? No matter how much charges sink into the Earth, it's so big that the potential does not change. So you could consider the whole Earth to be an big ideal conductor. That's why if you touch a live wire, you instantly get zapped, because the Earth is such a perfect conductor that current flows through you into the Earth, right? The Earth is a conductor. The only thing that would save you is if you're wearing rubber shoes. So you have something that prevents this sinking of charges from a high potential surface into the Earth. Okay. Example 4.14. This is a good example. This is kind of shows you how to reason about conductors. So if I have a charge Q, and then I have a conductor shell, spherical shell. Not a circle, this is a three-dimensional sphere. So this is conductor material. question is, what is the field outside the shell? What is the field inside this shell? And what is the charge distribution? So the shell has an interior diameter of A, has an exterior diameter of B. So the question is, what is the field here? What is the field here? What is the charge distribution here, rho SB? And what is the surface charge distribution here, rho SA? Given the principles that we already know, is this something we can solve? Yeah, it is. So what is E and V everywhere? And the thing is, the second thing we want to solve for, what is rho SA and rho SB? Okay, so we already know how to solve this. Gauss's law, right? So solution. So for R less than A, this is easy. I have a Gaussian surface here, radius R, right? So I know that E equals E times 4 pi R squared, E times the surface of the Gaussian surface, 4 pi R squared, equals enclosed charge, which is Q in this case, over epsilon naught. So that tells me that E equals Q over 4 pi epsilon naught R squared. Of course, this is expected. I'm expected to get the Coulomb force law, right? But in vector form, this is going to be, let's say, spherical coordinates, is going to be R hat Q over 4 pi epsilon naught R squared. This is for R less than or less than A. Okay, so what about R larger than B? In this case, my Gaussian surface will be this. Would the existence of the ideal conductor spherical shell matter in terms of applying Gauss's law? It will not matter at all. And the reason it will not matter at all is this is an ideal conductor surface. So although there is going to be charge distributions along the surface, there's going to be rho SA and rho SB. The total charge in all that's happening is that the charges are moving around. The total number of charges is not going to change. So if the conductor was in equilibrium before we put Q here, the conductor will remain in equilibrium. And the assumption here is that the conductor is in equilibrium. There are no charges added to the conductor. All that happened is the charge is redistributed. So the total enclosed charge is going to remain Q, because the total charge in the conductor, although charge is redistributed, the total charges in the conductor are still zero. Then the net charges in the conductor are still zero. So in this case, for R larger than B, it's still E equals Q over 4 pi epsilon naught R squared. This is for R larger than B. Because I apply Gauss's law and nothing changes. The enclosed charge is still Q. However, the field inside the conductor is zero. So if I plot in this case, but E equals 0 for R larger than A and less than B, because that's an ideal conductor. So if I plot E with respect to R, I get something like this. Until I reach A, and then the charge goes down to 0. And then at B, the charge goes back up, and then it goes down like this. Okay. And it's just that the field collapses inside the conductor and then goes back. What about the potential energy? Of course, there are many ways to calculate the potential energy. I can take this and I can apply the gradient. I can find a function that if I take its gradient, I get this, or I can just do direct integration. So for potential energy, I assume that V infinity is 0 as always. And I know that VB minus V infinity, which is 0, equals the integral of coming from infinity to B R hat Q over 4 pi epsilon naught R squared. This is E dot DL. DL is R hat DR. So this is DL. This is E. I just applied the integral formula for the potential, and use the knowledge that at V infinity, I want to set the potential to be 0. This is what VB is. So I just can easily do this integration. So VB is going to be take Q, all the constants out, 4 pi epsilon naught R squared. And then I'm integrating from infinity. I guess I could say, yeah, infinity to be integrating -1 over, take the minus sign n. So it's going to be -1 over R squared dr. And what does this integrate to? This becomes 1 over R B infinity. 1 over infinity is 0. So that doesn't matter. So I'm going to end up with 1 over B. Oh, there is no R squared there, of course. R squared was inside the integral. Okay, so VB is going to be Q over 4 pi epsilon naught B. Okay, so VR is going to be Q over 4 pi epsilon naught R. If you do this instead of specific B, you do it for specific R, for R larger than B. This is what the potential energy is for R larger than B. What about inside the conductor? Inside conductor, the potential will be the same. It will be the potential at VB. So inside the conductor, VR equals VB, which is this value here, where R is larger than A, less than B. So you always have the potential everywhere, almost. I want to find the potential now inside. For R less than A, what is the potential? Well, same deal. We have to go from infinity to A, E dot dl. This is an integral. I can always subdivide an integral. So I can divide this as going from minus infinity to B, E dot dl, right? Minus the integral going from B to A, E dot dl, right? And then minus the integral going from A to R, E dot dl. A to B, B to A is inside the conductor. So this is 0. Remember, because the conductor is an equipotential boundary region. This we already calculated, right? This is Q over 4 pi epsilon naught B. And then now we have to calculate this. If I calculate this integral, this turns out to be Q over 4 pi epsilon naught 1 over R minus 1 over A. This is a simple integral to calculate. It's the same as the calculation that we've done. We've done here. Okay. So VR equals Q over 4 pi epsilon naught 1 over B minus 1 over A plus 1 over R for R less than A. So now we are ready to plot V with respect to R. So it is some kind of inverse function, right, with respect to R. What happens when R gets to A? When R gets to A, I end up with 1 over A minus 1 over A. So I end up with V being Q over 4 pi epsilon naught B. This is equal to the potential at B. So the potential is going to become constant between A and B because it's a conductor. And then at B is going to start to go down again, like this. So this is what the potential as a function of R is going to look like. It's going to go down as an inverse function of R. At the boundary is going to become constant. And then once we leave the conductor, it's going to start going down again as an inverse function of R. What about the surface charge densities? Here we can apply Gauss's law. So we already know E and V everywhere, but we really don't need them to calculate the charge densities, right? Why? Because we can easily apply Gauss's law. So we have the conductors here. I'm gonna explode it so that it's clearer. So it could be a thin ring, right? So this is Q. And then I'm trying to find RSA and then RSB, rho SP, sorry. So I need only to do like a Gaussian surface here. Let me use this Gaussian surface. Let the Gaussian surface be a spherical shell in the middle of the conductor. So this is this red dotted surface is my Gaussian surface. So if I apply Gauss's law here on the surface, this is S. Rho S equals E dot ds. Now the beauty here is that I know that E is 0 inside the conductor. So this whole thing goes to 0. This has to be equal to Q enclosed over epsilon naught. This whole thing goes to 0. So 0 equals, what's Q enclosed? Q enclosed is Q internal charge over epsilon naught plus the charge on the inner surface of the conductor. What is the total charge in the inner surface of the conductor? It's rho S A times the surface area of the conductor, 4 pi A squared over epsilon naught. And that's it. And I can use this equation to solve for rho SA. So rho SA is going to equal minus Q over 4 pi A squared, Coulomb per meter squared. I didn't even have to solve for E. I just strategically put my Gaussian surface inside the conductor, knowing that E inside the conductor is 0. And this allowed me to kind of directly calculate rho SA from the charge in the middle. If there was no charge in the middle, of course, rho SA is going to be 0. What about the outer surface? Again, I can put my well, I don't even need to use Gauss's law. I can use the fact that total charge in conductor is 0. Here, one assumption, by the way, I want to make is that due to symmetry, because it's a spherical, the charge distribution is uniform. If this was not a spherical shell, the charge distribution, if it was like something with ragged, pointy edges, the charge distribution will not be the same everywhere. This only works because the charge distribution is equal on the surfaces, on each surface, everywhere, due to symmetry. But using the fact that total charge in the conductor is 0, we can say that the outer charge is rho SB times 4 pi B squared, plus the inside charge is rho SA times 4 pi A squared, needs to equal to 0. So this tells me I can take 4 pi out. This tells me that rho SB equals minus rho SA times A squared over B squared. I know already what rho SA is. It's this thing. So rho SB equals, and there's a minus sign here, so this cancels. This becomes Q. 4 pi A squared cancels with this A squared, and I end up with B squared. So this is rho SB. So I found the electrical fields everywhere, the potential everywhere, and charge distributions everywhere. Okay. Next thing we're going to talk about is dielectric materials, and I'm not going to get into it, but it will also it will fall back to the postulates, right? So the 1 and the 2 postulates, of course. Divergence E equals rho V over epsilon naught, and cross E equals 0. By the way, I can take the epsilon E to the other side, and I can write this in terms of the flux density vector. Divergence D equals 0. This has much simpler form with the flux density vector. There is no more epsilon to worry about. Okay, so sharing. So I'm going to continue this discussion on dielectric materials on Monday. It's an interesting discussion. And I would say it is the core of electrostatics. It's an important discussion. All right, guys, have a nice weekend and I'll see you on Monday. Bye.